Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistance, and today we are looking at solubility. Specifically, what we're looking at is how to identify whether two different substances are in fact soluble with one another, whether a solute can dissolve in a solvent. And there's one guiding principle that you need to recall whenever addressing these kinds of questions, is that like dissolves like. If you remember that, then the rest of it is all about just simple dipole moments in geometry. So when I say like dissolves like, molecules can generally be broken up into two groups. You have your polar molecules and your nonpolar molecules. Nonpolar molecules are molecules that either have no dipole moment because there is no difference in electronegativity between the two atoms, as is the case with diatomic molecules, such as F2, Br2, Cl2, H2, and the like. Similarly, you can look at nonpolar molecules as molecules wherein their dipoles cancel one another out. So a good example of this would be a tetrahedral molecule wherein the species surrounding the center atom are all the same. They're all going to pull in the same manner with one another, and the angles all being equal will result in a canceling, and there will be no actual dipole moment. There won't be a shift or a pull to one side. The other type are polar molecules, and that is instances where you have molecules that the species have differences in electronegativity and they don't cancel one another out due to the geometry. So let's take a look at our species here. We have diatomic chlorine. That is very evidently a nonpolar molecule. The two chlorines have the same electronegativity, so there is not going to even be the dipole in order to draw the electrons to one side or the other. So because there is no dipole, this is a nonpolar molecule. So we're going to mark it as nonpolar, NP. Let's look at water. Water is H2O. And with that, we've got our oxygen and two hydrogens. And if you recall, it's a bent molecule. So you'll have two lone pairs and a resulting dipole a resulting dipole that goes like so. So this would be considered a polar molecule. We'll just put a P for polar. The last one we have is toluene. Toluene you may not be familiar with quite yet, but it's C7H8, and it looks something like this. When I draw organic molecules, specifically hydrocarbons, each of the corners is going to be representing a carbon, and the hydrogens are generally implied, but I'm going to write this out explicitly so that it's easier to see. We're going to start by drawing the carbons. So there's going to be a carbon over here, and it's going to be single bonded to another carbon, which is double bonded to another carbon, who is single bonded to another carbon, and double bonded to another carbon. We're alternating our double and single bonds. And now we can fill in our hydrogens. We'll do that in blue. So we have the space for 3 hydrogens here. And there are no hydrogens on the next carbon down, just below this one, but there's 1 on each of the other carbons. And we know this because carbon makes 4 bonds, and each of the other carbons has only 3 bonds. And if you count this up, you will find that there are 5 carbons on the ring, 5 hydrogens on the ring, and 3 on the substituent carbon. That's a total for 8. And it's a 6 carbon ring with 1 carbon as the substituent, which makes it 7 carbons. So that's toluene. And the big thing to recall with hydrocarbons is the difference in electronegativity between hydrogen and carbon is very small. And the geometry of this particular molecule is such that all of these hydrogens, what little there is, you're going to be drawing it toward the center. So those kind of cancel out, and you would be tempted to say that it all shifts up toward the substituent. However, the substituent also has all these little dipoles on it that cancel out, and the result is a nonpolar molecule. So we're going to put NP. So chlorine, diatomic chlorine, would dissolve in toluene. Let's take a look at another example. We're given sodium fluoride in methane and in ammonia. Well, sodium fluoride is not a molecule, it's an ionic compound. But because it's an ionic compound, it's ionic, but it's also polar. And methane, as we demonstrated with toluene, methane is CH4. It's a tetrahedral, and all of the hydrogens are evenly spaced. They all cancel each other out with their dipoles, so methane would be nonpolar. And ammonia, if you recall, ammonia is NH3. So you've got these hydrogens here, here, and here. And then you also have a lone pair over here. And so this lone pair turns this ammonia into a polar molecule. So sodium fluoride would dissolve in a ammonia. Similarly, sodium fluoride would feasibly dissolve in water and in other polar molecules, polar solvents. Last one is acetic acid, which, if you don't know the formula for that, it's CH3COOH. That's acetic acid. And that is a polar molecule. Now, we can demonstrate this fairly easily. We can draw it out. So we've got a carbon, and to that carbon we have 4 hydrogens, or 3 hydrogens rather. So hydrogen, hydrogen, and hydrogen. So they're all canceling each other out with their dipoles. And then we have another carbon over here. And to that carbon, there's an oxygen and a hydrogen, an OH group, and it's also double bonded to another oxygen. And with that, you have 2 lone pairs, and also on this one, you're going to have 2 lone pairs. So these lone pairs on the oxygens are pulling first of all, oxygen has a electronegativity that is different from carbon, so it's pulling toward oxygen to begin with, and those lone pairs are also helping to create a dipole moment, making this a polar molecule. So this is polar. Now, carbon tetrachloride is just like methane, except instead of hydrogens, it has chlorines. So carbon tetrachloride is going to look kind of like that in its 2D representation. So that is a very nonpolar molecule. And finally, we have water. Water, as we saw before, is a polar molecule. So we're just going to put a P over here. So if you were to look at this, acetic acid would dissolve in water, but not in carbon tetrachloride, which makes sense because acetic acid is what you find in vinegar, and vinegar is can dissolve in water and is soluble in water. So in general, these are the things that you want to look out for when determining what is soluble, what solutes are soluble in which solvent.